Hey everybody, it's Mr. Mott. What we're going to do is go through our determination of the molar mass of an unknown weak acid. In this case, we used Mandelic acid. The fact that we know the identity of it is actually the purpose of the experiment and to determine the molar mass of it. However, typically you would not be told the identity of the unknown weak acid so that you wouldn't be influenced by what the internet tells you that the molar mass is based upon your results. Prior to this, what we had done is that we had determined the concentration of our sodium hydroxide solution, which is here, and then we had weighed out 0.2244 grams of our unknown acid. The first picture that we see is the titration curve. And something to kind of note is that on the upper right-hand side of our LabQuest screen, we see the pH. That pH is whatever the pH is at whatever volume that that we happen to have selected. Right now, we're at zero. We're at a zero volume, which means we haven't added any sodium hydroxide. All that really means is that the pH of our solution of our unknown acid is around 2.46. So that's sort of in line with probably lots of weak acids that we are somewhere above 1 for a weak acid to start out with. Now the thing that we are trying to determine is that inflection point where our graph sort of goes from turning one way to turning another way, and it's somewhere in this area. And it's really hard to just sort of use our eyes to be able to figure out what that is very accurately. So what we do is that we take the second derivative of this curve in this, and we look in this area. So this second, so what I've done is I went under the table, I created a new calculated column and came up with the second derivative. And here's what it looks like. It looks like this sort of what I call sort of this almost like a heartbeat rhythm on EKG meter. So it would go up and it kind of comes down and it goes flat again. And what we use the LabQuest to be able to do is figure out at what point do we cross this, this x-axis here. So what we try to do is that we try to, if we have a data point, we can just select that data point that if it's right on the line, but we don't have a data point that's on the line. And that would tell you the volume that we were at that inflection point. So since we didn't have that, what we had done is that we had selected this area, which is that's kind of darkened, and we drew a line of best fit through some of these data points. Then we interpolated, we drew a line of best fit, and we interpolated, and we used our buttons here and here to try to get a point of our second derivative really close to zero. And that's what we have around the box. That's as close as to zero as I could get. So that's what this box is telling us. That box is this value here. But the value that we're interested in is the volume at that inflection point where it changes direction. So this 14.704 milliliters, this is the endpoint or the equivalence point. So that's how we determine the volume at the equivalence point using the second derivative. Now what we have to do is actually go back to our original titration curve, find the pH at this volume. Okay, so let's take a look at that now. So it happened to be that I had a data point right at like 14.7. Since the inflection point was set 14.704, it's pretty much the same. So I selected that data point here, which is reflected down on the bottom right, and it says that at my endpoint or my equivalence point, the pH is 8.7. Okay, so that's a really helpful idea that we need to know. So the next thing that we would need to know then, or you'd be asked to do, is find out what is the pKa. And so for that, we have to sort of use this information that our equivalence point is at 14.7. Okay, so let's take a look at our next graph. According to our Henderson-Hasselbalch equation on the right, the pH is going to equal to pKa when this value here is 0. Well, halfway to the equivalence point on our graph, what happens is that the weak acid that we are titrating represented in our formula by HA, half of it is gone. So halfway to the endpoint, which is on the graph, is half of 14.7, around 7.35. Halfway to the equivalence point, half of my acid is gone and it's been converted to its conjugate base. So it means that these two values are equal. And if A minus and HA are equal, this value is 1. The log of 1 is 0. So halfway to the equivalence point, what you get is you get the pH is equal to the pKa. So what I did in order to find that out, to find out what pH on my graph, what is the pH halfway to the equivalence point, I needed to find a value of about 7.35. I didn't have a data point for that because I was adding 1 milliliter a time during this time. So what I did is I selected this region, this darkened region here, and then I drew a line of best fit through here, and again I interpolated, and I got to a volume of 7.35, and at that volume, this is the pH. So again, halfway to the equivalence point, the pH is equal to the pKa. All right? So that really tells you a lot of what you need to know for the data analysis for our lab. All right? And then you'd want to be able to convert from the pKa to the Ka is one of the things that you're being asked to do. And then something to think about kind of, throughout this kind of whole process is that you're titrating a weak acid with a strong base. These are reacting in a 1-to-1 ratio. So as far as like your other calculations that you need, you want to think about your ultimate goal is to find the molar mass of your unknown acid. For your molar mass, you need grams and you need moles. Okay? We can't take, and we had 0.2244 grams of our weak acid. We cannot convert from these grams into moles using molar mass because you really don't know what that is. That's what you're trying to find out. This is the end goal. You know the mass, which is how much we started with. You need to figure out how many moles of your weak acid that were originally present. And that isn't something that you can measure directly, again, because you don't know in theory, you don't know the identity of your weak acid. But what we do know is that the weak acid reacts in a 1-to-1 ratio with the sodium hydroxide. That is something that was given to you in the write-up. So what you can do is that you can figure out your moles of your NaOH. You can use the molarity and you can use your volume to figure out your moles of NaOH. Your moles of your NaOH and the moles of your weak acid are the same at the equivalence point or the end point. All right? This is the whole key here. All right? Hopefully that was helpful. Thanks for watching.